Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the SAT SMT workshop. It's Friday afternoon. It's the last day. It's late, I know. So we have a free talk. Nicolas Bionner will present his work on SMT solving for applications. João Marques Silva will present his recent work on max SAT optimization. And he will also present some application, I guess. And I will finish with a short overview of knowledge sharing in parallel SAT. So each talk is about 30 minutes. So it's a workshop, so feel free, I guess, to interrupt because we have no deadline at the end of the day. It's the last session of the conference. So even if we overshoot the 90 minutes which were allocated, there is no problem with that. Okay, I hope the speakers are okay with that as well. Yes. So before the talk, two announcements. The first one is that this summer there is the first SAT SMT summer school, which is organized at the MIT. It is organized by several people. The main organizer is Dr. Vijay Ganesh. It will be in June, from the 12th to the 17th of June. And you will have, I think, something like 35 talks, 35 lectures. Each one is about 1 hour something, 1 hour 15, I think. And it will give an overview of SAT, SMT, theory, the application. And it's really made for people who want to know more about that, people who know a lot, who already have some understanding. And of course, it's there to encourage discussion and to try to push the technology and the research in that domain. So you can register online if you go to, well, if you type SAT SMT on your search engine, you will find, I think, the summer school. And the speaker today will all present in that school as well. The second announcement is something which has been decided recently. We have decided at Microsoft Research to do a special interest group on Z3, on the Z3 SMT solver, which is done in Microsoft Research. We have several objectives. We want to find a way to structure the existing base of user of Z3. We want to have a forum where they will be able to share practical experience, practical problem, and we hope that it will be beneficial. And of course, we want to use this SIG to eventually get input about possible evolution of the solver, etc. And the last objective eventually will be to make the technology more visible, but not just on the research, but maybe for people who can really benefit from it at a practical level, like consultant, engineer, etc. The format will be that we will organize meetings, so we should have 2 meetings a year. And you will see a call for participation, which will come in the usual channel, like the SAT Live and SMT mailing list, etc. So the talk, I mean, the meeting will be quite informal. As I said earlier, the goal is to discuss, present practical problem and solution. And we will have some funding for students who want to attend, some funding for traveling. So as I said, next step, we will announce the SIG on the classical channel. And there is one contact point for this SIG, which is Christophe Wintersteger, who works with me in Cambridge. So if you want some information today, you can ask me, but later on, we will push information, and Christophe will be the main contact point. So I think I'm done. Now we can move to the first talk, which is Nikolai. I'll let you plug it.
Thank you. First, thanks a lot, Joseph, both for organizing this session and as well as the wonderful idea with the special interest group. So you would show a special interest in this talk as well. So I will give, the following will be a somewhat high-level overview of some of uses and facilities available from Z3, but I will end off with a small newer feature that we're working on. So there will be a very slight technical angle to the talk, but only in the end. So the agenda for the talk will be refreshing what is SMT, and given the many familiar faces in the audience, I've made it to a one slide. And there's also one slide on what is Z3, but then more slides on who use Z3 and what facilities are useful, what APIs and what theories are useful in Z3. I'll give us some overview of that. And then, as promised, end off with a small appetizer to which directions we're taking Z3 in currently. Okay, what is SMT? Actually, two slides. Here's the, it's whether the input to an SMT solver is a first-order formula over using symbols from one or more theories. And at the core of the SMT solvers is that they have specialized algorithms for these to solve for satisfiability modulo the theories. So here's an example formula that mixes it combines three theories. The first one is the theory of arithmetic, and you see the symbols that have plus and minus involving x and y. And the second theory involved is the theory of arrays, applicative maps if you want, where I've given two of the axioms that are relevant for this formula, namely that once you update an array with an index I with the value of v, and you access it at the same index, you get back the value of v. And otherwise, if you read at a different index, the read propagates in over updates. The third theory involved in this slide is theory of uninterpreted functions. So f here is any function symbol. Now this formula happens to be valid, and an SMT solver can deduce this by integrating solvers for arrays and arithmetic and congruence closure for function symbols. Okay. In context, SMT solvers build upon two technologies developed in two areas, namely in propositional satisfiability solving and in first-order theorem proving. So here's an example of a propositional formula, as well as a set of group theory axioms hinting that first-order theorem provers, here you encode theories such as group theory directly in first-order logic. The last example gives an SMT formula similar to the one in the previous slide. So the theory of arithmetic and arrays is implicit in the background. But we build upon advances within SAT and first-order theorem proving, and to give some idea of some of the quite recent but dramatic improvements in satisfiability, I've borrowed a slide from Daniel Lebert that illustrates progress in SAT solvers over the last 8 years. On a given set of benchmarks, they run the winners of the SAT races and second or the top systems from the SAT races, and we see that the system anno 2002 gave up after solving about 45 problems the newer systems spend less than maybe 10 seconds on the first 45 problems. And they spend less than 200 seconds on the first 120 problems. Just to illustrate, there are a number of techniques that are developed within SAT solving that bring new improvements almost every year that one could characterize as milestones. First order theorem proving has a long and proud tradition, and Andrei Voronkov helped supply a summary of some of the milestones in first order theorem proving, and it goes back to the 1930s. And there are still distinct milestones being advances being made these days, primarily in context of reasoning in large ontologies, how to select axioms that are relevant. But to illustrate some of the success stories in first order theorem proving, here's one success story, which is proving that this axiom is a single axiom of equivalence. We could contrast that with what are the problems that SMT solvers are exercised at. These are not the kind of problems that we are tuning SMT solving for. So here's a slide on milestones in SMT solving, and it has shameless inputs from our own work on Z3. So, two sets of benchmarks that driven progress in quantifier instantiation reasoning have been Boogie benchmarks obtained from Rustan in his regression for Boogie. We were able to get the hardest benchmark to run in less than a second, and in 2007. But these benchmarks are relatively small compared to what the VCC project exercised Z3 with. So this graph illustrates the regression suite of the VCC project and how much time the regression suite took over different updates to Z3 versus different axiomatizations. As you can see, Z3 contains a SAT solver, but it's a fairly small component in the overall picture. It's less than 10% of the effort. And nevertheless, it's still a central component, and we inherit progress in SAT solvers. So what is Z3? Essentially, it's a combination of little engines of proof, comprising of congruence closure, quantifier elimination procedures, solvers for arrays and data types, and arithmetic, bit vectors, and so on. And you can download it from this link below. Now, who use Z3? One way to get an overview is going to RISE for fun, and there's a diagram of tools in the RISE group. And this diagram shows the dependencies between the different tools. So here you can see which tools use Z3. So several of them use the Boogie verification tool that generates verification conditions. Others go directly to Z3, such as formula and automata tools. Here's a different overview of tools that use Z3. And I've roughly, and again shamelessly, categorized them in three buckets. One bucket is property-driven tools. They take a property and then enhance the property or dice the property in order to establish it over a program. Others are take a starting point executions and refine properties based on execution traces and simulations. And then a third class of tools are model-based. They don't start with the end product program, but they use models to either derive programs or to test programs with. So the Microsoft tools are then roughly categorized according to these. So here you have the verification tools, you have SLAM and Yogi and Pix and Sage in the execution guided tools, and then there are a number of model-based tools. This gives some idea that there are many different areas that can use SMT solvers. And they also use quite different features. So here's an overview of some of the tools and which engines, so which theories and core capabilities of the tool they use, as well as which APIs, which interfaces they interact with. So you can see that common to essentially all tools is that they use models, they use counterexamples as a feedback, but they are quite different in whether they use, say, quantifiers or arrays and bit vectors. You almost don't find any tool that uses all features. Pix is probably one of the tools that use most features. Formula as well. And then there's proofs. And in fact, none of our internal tools use the proofs, but there's Isabel and Halfor and Charek Weber is in the audience who has been exercising this. It's to illustrate that there are many ways to plug and maybe play or sweat with the SAT3. Three tools that I don't think have been mentioned here, but I think there are quite important uses of SAT3. One is Sage, which generates test cases, is a dynamic simulation tool. It's used internally to derive fuzz tests. And we claim that it's the biggest use of any SMT tool or solver in number of constraints churned through. Another application of SAT3 has been in a verified operating system kernel called Verve, which is a small operating system kernel. And this is a project of Chris Habwissel of Microsoft Redmond. And they have split the type safety problem of the operating system kernel into two parts. One is by piggybacking on a typed assembly language using compilation to ensure type safety and from type-safe languages. Another is for the remaining code that's in assembly is to then encode it into Boogie SAT3. And that gives a feasible type safety verification project. The last tool I want to highlight is the Rex tool. It allows to explore regular expressions. So it encodes regular automata as constraints and then does automata subset checking, which is p-space complete, using SAT3 as a constraint solving problem. It's available on Rise for Fun, and here you can go on Ask Rex, and it gives counter examples and pictures of automata. Okay, how to use SAT3? So as illustrated on the slide with tools using APIs versus engines and theories, here I call them theories. The main theories that are exposed are that for uninterpreted functions. There's each of these you can try online. So here's an example with an uninterpreted function f that takes a sort A and returns sort A. And there's a constant small a. And if we assert that if f of a equals a, and we also assert that a equals f of a, so f 3 times, then these two equalities are by themselves satisfiable. They're not don't introduce any contradictions. But we can add a contradiction by asserting that a is different from f of a, which which is not clearly an instance here, but it follows by congruence closure, namely that the applications of f are relatively prime, and then enforce that a equals indeed f of a, and so there's only one element. So if you run this online, you will get a model for the first two assertions before you add the third assertion. So this is a model for the two first equalities, and the model gives a function graph for f. So f here is defined as a function that takes an argument x1, and it essentially always returns the same value. It has an if-then-else statement, but that's our model construction is not minimal, doesn't minimally reduce the function, a graph that it produces. On the other hand, after you have the disequality, the assertion is unsatisfiable. And I'll not demo all of the samples, but just illustrate that you can also do arithmetic. So here's a scheduling problem, and the slides will be available, and you can essentially click on the links to run through the samples. Here's a sample with bit vectors, with the theory of bit vectors. They are declared in the SMT2 lib interchange format, which is a standardized format for exchanging formulas. There's algebraic data types. So here's an example where we declare the type of lists, integer lists, and then introduce two constants, L1 and L2, that range over lists. Now we assert that L1 and L2 are neither nil, and that their heads coincide and tails coincide. And we assert that L1 is different from L2. Now that's not satisfiable in the theory of lists, so the answer will be unset. For the theory of arrays, we support the usual McCarthy theory of arrays that was also in the initial example, but also extensions to arrays where you can map functions over the range elements. Finally, one can extend Z3 with user theories. So we have a facility for plugging in your favorite theory, say, would it be of Q's or of Boolean algebra with Pressburg arithmetic or other theories. Now this is done programmatically, so you have to implement a solver, and it's not for the faint of heart. From the API standpoint, the main interaction models is to supply assertions and then extract back a model, as illustrated with the uninterpreted functions. The other main interaction model is to retrieve back proof objects. So here's an example where Z3 produces a proof and prints it for a somewhat small or trivial theorem. And this is used, as I said, in the context of Isabelle and Hull 4. So using Z3 as an untrusted oracle. These provers can then rerun and check the proof objects, whether they're really evidence. You can also use Z3 for algebraic simplification. So this is used in the context of the SLAM tool and Yogi that maintain formulas and then ask to simplify them algebraically to compress the representation. You can ask for which equalities are implied by a set of constraints. So here's an example where we assert that x is greater than equal to y, z is greater than equal to x, and y is greater than equal to z. So there's a cycle of inequalities. So these three variables will all be equal. In every model for these assertions, these will all be equal. And now we supply 4 terms and ask what are the partitions of these 4 terms. Now the terms supplied here and here are compound, so they add z and y, but it will follow from these equalities that z plus y and x plus z are equal as terms. And this is the information you get back from this list of integers. They are numbers of partitions. And this is used in this layer tool. There's facilities for Pressburg arithmetic, quantifier elimination, and quantifier elimination for algebraic data types, which one can use as a simplification. And you can extract the minimal or a subset of assertions that are inconsistent. So in this example, not all of these assertions are inconsistent, required for an inconsistency. So the unsatisfiable core will extract the subset that was used to derive the inconsistency. Okay, so now to the news. What is new in Z3? So what are we up to? So the main theme of our ongoing work is, I think, can be captured as enabling functionality that's used by external components internally within Z3. So the current, what we're observing from users is that the current interaction with the tool is, with the external tool, is to supply Z3 with constraints, get feedback in terms of a model or otherwise, and then generate new constraints to guide, search, or to refine as a refinement of the existing constraints in order to implement the semantics that's relevant to the tool. But what we want to do is to essentially supply enhanced control over Z3 such that external tools can exercise this control directly on Z3, but limit the pipeline of constraints to a single call. So the elements used in this dream includes user solvers, but also adding tactic facilities for giving finer grained control of how search can proceed. There's a facility that we call model-based quantifier instantiation that I will go through. And then there is a facility for giving fixed point semantics to formulas. So the usual semantics of first order SMT is classical first order logic. And this requires users who want to encode reachability to go through various hoops. So so an overview, the slides gives an overview of these two components, the model-based quantifier instantiation and the fixed point component. There's demos of both of them online, and the links are embedded in the slide. I will go through the model-based quantifier instantiation by an example. So here's a motivation for it. Suppose we have the following while loop with a precondition, a test, and a transition within the while loop, and a postcondition. We wish to establish that the postcondition holds whenever the while loop is exited. So in standard verification of inductive verifications, the problem is to find an inductive assertion I that holds after the precondition is met. I is furthermore inductive, and then when the loop condition does not hold, that together with I implies the postcondition. So so if we can find an interpretation for I such that phi sub I, this formula on the right-hand side, is satisfiable, then the post condition holds. So this is, in a nutshell, turning invariant generation or invariant synthesis into a satisfiability problem. So here's an example, very simple loop that increments x by 1 and y by 2, and by the end of the while loop, y equals 2 times n. And transliterating this while loop into the template form in the previous slide, you get this formula. Okay, so again, if phi sub I is satisfiable, then the post condition holds. So how do we synthesize the inductive assertion? Well, we could try with an initial model. Suppose we said let I be the predicate that's true everywhere. What then? Well, then we can check, say, one of the conjuncts. Let's check the last conjunct in this formula with respect to this model M that we call M. Well, checking it with respect to that model M is to replace I by the interpretation under M, which is the predicate true, and then we can check the validity of this universally quantified formula by dually checking unsatisfiability of the negated formula where x, y, and n, the bound variables, are now existential force, so they are free. Okay, so we can turn model checking of a quantifier into satisfiability checking, assuming that we have a partial interpretation. So let's try this idea. Well, before we try this idea, then we see that actually this formula is not unsatisfiable. It's satisfiable if we set x to y to n to 1. So this is not a good model. This is not a good interpretation for the formula. But we could try to refine this, run this process, and essentially add the counterexamples we meet and exclude them from the interpretation of I. And we can do this in as much as we want, and we will end up nowhere. Okay, so we need something more. So the idea here is to add a template macro for I. So let's introduce new constants A, B, C, and D. So these are symbolic constants. And then let's guess that I is equivalent to some linear inequalities using these new fresh constants. And so now we have actually a macro for I. This can be detected as a macro for I. And we can then model check, use the same procedure, the model-based quantifier instantiation. So model check for satisfiability of the quantifier-free version of this until we get to a model, a model. So let me just give a demo of this to show that it's realistic, that it's not smoke and mirrors what I'm talking about. So let's. So here's the example invariant loop invariant in SMT2lib format, and I've supplied a template for I, and the sufficient template in this case happens to be we introduce one equality and one inequality, where my mouse is over, using finite domain, so constants A1, B1, C1, and D1 that in this case range over small bit vectors. So there's a finite number of choices for these coefficients. And that gives a search space for what invariants we can synthesize for this loop. And so now we can ask whether this formula is satisfiable. And indeed, Z3 finds a model and it's it's a bit hairy, but it's a model that establishes the invariant. So it essentially says that let's see, y equals 2 times x. It's a loop invariant, and that x is less than or equal to n is also part of the required invariant. So I needed an equality and a disequality. Now, in principle, one can augment a template with as many equalities and disequalities as are required. So that's the demo, and now to the conclusions. So we started out with the current main applications, the test case generation, verification, model checking, and model-based tools. New applications keep appearing. Synthesis, compiler optimization points to analysis in the context of the fixed point extensions. Analysis of real-time systems, the quantifier elimination procedure is used for that. And our ongoing efforts are performance and scale and expressibility and scriptability and extending, giving access to the solver programmatic access. Okay, thank you.
So we can take some questions.
Bogart.
Very low-level question. Is it possible? Is it possible to send to Z3 incrementally a background theory? So having push of several axioms, skip a block, add a theory that you want. So for the moment, we just always start a new Z3 instance.
Right. So the question is whether it's possible to push a background theory, so axioms incrementally, and there are two ways this incrementality can be achieved. So one is over the say standard API by maintaining scopes and checking satisfiability. Now add new axioms depending on whether the answer is still satisfiable. So you can also use the model that's generated to inspect which axioms should be added. But you could also integrate this incrementality more tightly as a user theory. So in fact, user-supplied theories have the ability to inspect the current state of the search by knowing which which literals are assigned to what values, and they can so on the fly they can add new facts to prune branches during search. Yes?
Yes, one second. So, just a simple question. I would really love to license this technology from you on a commercial basis.
Yeah.
Do you have plans to make this commercially licensed in a way that I can use and sell?
If you want to send an email, and we can.
Okay.
It will be. We don't have a preset process, but we'll have to ask our license person what. So we need to give them an idea of who they should have an idea what it's worth for you, right? And how little work they can it would require to do it. And if it's a lot of overhead to get a license, then it's not. But I think it's an ad hoc process. So you ask, and we'll look into it.
Any questions? Yeah.
I was wondering what the plans are
Excuse me. Sorry, but very cold.
I can repeat the question.
Anticipating the talk in this session coming later on parallel SAT, I guess, what are the plans for parallel implementations of Z3? How is that going?
Oh, well, it's going very well. Christoph Wintersteiger has been working on it both when he was intern with Josef and Leonardo some years ago, and now he's postdoc at Cambridge, and he's been setting up Z3 on our cluster quite aggressive.
I'll ask the dirty question. So how many beers do I have to buy you to get regular builds on other platforms? Because I'm a little tired of running Z3 inside of wine all the time.
Yeah.
I take a performance hit.
I see. Yeah, that's not in my control.
So whose control is it in? So I can buy them beer.
I see. It's an interesting question. Thank you.
So we'll take question later.
But you should upgrade to Windows. That will help.
So we switch to optimization with João Marques Silva from University College Dublin. We'll talk about Boolean-based optimization, algorithm, and applications.
Okay, thank you very much. Good afternoon, everyone. I'd like to start by thank you, Josef, for the invitation and for this very nice conference. I'd like to start to why should we talk about optimization at the Software Summit? And I have a small example, which is the following. Suppose, well, I'm not familiarized with Windows, so I'm going to give the example for the Mac or for Linux. Suppose you have a universe of packages, P1, etc., Pn, and we start by associating with which package a variable, a Boolean variable, which is 1 if the package is installed. And as I assume all of you are familiar, basically we can associate with each package a set of constraints. So basically, a package has dependencies. So if I'm going to install package P, there are some things I also have to install. And if I'm going to install package P, there are things that are going to be conflicting with my package. So basically, I represent them with two sets. And one problem we can ask is, okay, so suppose I want to install the largest possible number of packages. How do I do that? Okay? And basically, suppose this example. So basically, what I'm saying here is, for example, P1. If I'm going to install P1, I need to install P2 or P3, and I cannot install P4. And if I'm going to install P2, I need to install P3, and I cannot install P4. And for P3, I need to install P2, and I have no conflicts. And finally, for P4, I need to install P2 and P3, and I have no conflicts. So the question is, how do we model this? And one solution is basically what we call pseudo-Boolean formulation. So we associate with each package a variable, a Boolean variable, x1 to x4, and we would like to install as many packages as possible. Okay? So this is represented as a cost function. And then we have a bunch of constraints, saying, for example, if I'm going to install package 1, then I need to install P2 or P3, which is shown there. And if I'm going to install package 1, then I cannot install package 4, and etc., etc., etc. So, for example, probably the most interesting is if I'm going to install X3, then I need to install, X4, package 4, I need to install package 2 and package 3. Okay? So basically, this is my optimization problem. So Boolean variables and a set of Boolean constraints. Okay? And so I hope with this small example, I motivated why optimization could be interesting for software development. Of course, I have a few more examples. This is the first example. So this leads me to the outline of the talk. I will define what is Boolean-based optimization. There are different flavors, and so I would like to start by presenting the different flavors. Then I'll go into a few more applications. Then talk about algorithms. And throughout this, I'll be talking about encodings many times. And so I will go into some details here of encodings. And finally, I conclude. Okay? So what is Boolean-based optimization? Basically, it can be many things, and I'm going to show several examples. But the bottom line is we are going to do some linear optimization over Boolean domains. Okay? Actually, when I say linear, in some cases we allow it to be mildly nonlinear by accepting Boolean operators. But in general, we say it's linear optimization. So, and of course, there are many different instantiations developed over the last 50 years, more or less. Okay? So you can do what's called Maxim Satisfiability, and I'm going to talk about what this is. And you can do pseudo-Boolean optimization, and I'm also going to talk about what this is. But then you can also talk about weighted Boolean optimization, which is yet another variant. And the bottom line is you can map any of these problems to any of the other problems. So actually, it doesn't matter, but of course, the algorithms are slightly different. And of course, if you are wondering why is this important for you, for example, you can do optimization in SMT. For example, the name is Max SMT. And I'm not sure if Z3 offers that, but YAGS, for example, does Max SMT. You can do optimization in constraint satisfaction problems, Max CSP. And of course, you can do integer linear programming. Okay?
It's a sample. You can do it on top of the API.
Okay. So thank you. So basically, Max SMT is now available in different SMT solvers. So just to illustrate, and of course, what is called Max SMT is an instantiation of Maxim Satisfiability. So let's start with what is Maxim Satisfiability. So I have an example, and so these are clauses. And of course, after the first talk, everybody knows what the clause is. And I would like to satisfy all the clauses. So I have 3 by 4, 12 clauses. This is what I would like to satisfy. And of course, it's easy to show it is not possible to satisfy the 12 clauses. So it's just look at this example. So we can do resolution between the first 2 clauses. Yes, we get not x2. Then we can do resolution between the last 2 clauses. We get not x5, and then we use not x2 and not x5 to resolve away the mid clauses. So we get the bottom. Okay. And so what is MaxSat or Maxim Satisfiability is basically I would like to maximize the number of satisfied clauses. Find an assignment that maximizes the things I can satisfy. And for this example, we'll show later in the talk, the maximum we can do is 10. Okay? Now, of course, we can use this to solve many different optimization problems, and that's what I'm going to talk about. But before that, there are a number of variants of MaxSat, and let me quickly go over them. So what I discussed in the previous slide is what's called MaxSat. So all clauses are soft, so I have the freedom to satisfy or not satisfy them. And again, the goal is maximize the things I'm going to satisfy. Partial MaxSat is slightly different. Some things I have to satisfy, and others I would like to satisfy. So the things I have to satisfy are called hard clauses. The things I would like to satisfy are called soft clauses. And my objective is maximize the number of soft clauses that I'm satisfying. Okay? And then I have weighted variants. Basically, I can associate weighted with the clauses. And basically, I want to satisfy the sum of the weights of the clauses I'm satisfying. And in the weighted partial version, I also have hard clauses, and those are clauses that I have to satisfy. Okay, so let me continue. Now, another problem I mentioned before is pseudo-Boolean constraints and optimization. So what is a pseudo-Boolean constraint? Actually, I assume most of you have seen this in the past with a different name. So basically, we have Boolean variables, and we define linear inequalities on those Boolean variables. How are the inequalities defined? Basically, I have a weighted sum of literals, which can either be a variable or its complement, and I want that to be larger than some right-hand side. Okay? Now, I'm assuming all the coefficients, aij's and bi's, are positive, and it's easy to show that you can map any possible linear inequality with over Boolean variables to this form. So how do we solve this problem? Well, 2 ways. We encode everything to a causal form, like SMT was doing 10 years ago, or we can adapt the SAT solver and handle the constraints natively. What is the best way? Actually, in contrast to SMT, right now, the best way is still to encode to causal form. So what is pseudo-Boolean optimization? Is basically satisfy pseudo-Boolean constraints subject to a linear cost function. Okay, so this is the objective. And we are going to show next that the 2 problems are essentially, I can map one to the other. So the challenge is, suppose I give you this pseudo-Boolean optimization problem. Again, I have the constraints and the cost function. And the question is, how do I go from here to MaxSat? Any ideas? Okay, so it's like this. weighted partial max-SAT formulation. Basically, all these constraints are going to be my hard clauses. And again, it's easy to do. I can convert suitable constraints to SAT. It's well known. Okay? And so how do I handle the cost function? Basically, I have weighted soft clauses where each clause has a weight corresponding to its coefficient. Okay? So basically, since I'm trying to minimize, I would like to have not xj. What's the advantage of having that? It's Cj. Okay? And of course, if all the coefficients are 1, then it's partial max-SAT because then I don't have any weights. Okay, so it's very easy to do. And of course, I can go the other way around, and I'm going to show examples of that later on. Okay, so let's see some practical applications of Boolean-based optimization. So again, we have the software package upgrades, but now let's see how we do it with max-SAT. So again, we have the universe of software packages, we have dependencies, conflicts, and we would like to install as many packages as possible. Okay, and so basically now we model slightly different. So the package constraints are going to be my hard clauses. I have to satisfy all the package constraints. I cannot have any conflicts, basically. And if I'm going to install a package, all dependencies have to be installed. Okay. So again, this is my example, and I forgot to say. So the soft clauses are just clauses xi. What does this mean? Basically, I would like to install as many packages as possible. Okay. So how do I model that with max-SAT? Well, suddenly it seems very different, but actually it's exactly the same as I did before. So I have my hard clauses, exactly the same now in clausal form. And then the soft clauses are just unit clauses saying I would like to install as many packages as possible. Okay? Now, okay, so suppose you think, okay, this is too much detail. I would like a simple problem. So let's talk about minimum cover, so minimum vertex cover. Everybody knows what the minimum vertex cover is, right? Yes? Okay, so how do we model that with max-SAT? Basically, you start with a graph, and by definition, a vertex cover is a subset of the vertices such that every edge touches one of those vertices. Yes? So what is a minimum vertex cover? Basically, it's a vertex cover of minimum size. So the question is, so for this graph here, what is the vertex cover, the minimum vertex cover? Come on. Joe, please, anyone. What is the minimum vertex cover for this graph? 1, right? Which pick V1, right? Yes. So how do we model this? Basically, we associate a variable xi with each vertex, okay, such that if the variable is true, then I'm selecting the vertex to be in the cover. Otherwise, it's not. And then the hard clauses are basically saying that for each edge, either one of the vertices has to be in the cover. Yes, very easy. And what are the soft clauses? Basically, ideally, I would like not to have any vertices at all in the cover, right? So I prefer not to include vertices if I can. If I can, of course, in some cases I cannot. So in this case, this is my hard clauses, and then my soft clauses as before, very similar. Okay? Now the question is, so what is the solution? As you said, as a couple of you said, so the solution is, well, we basically put x1 to 1, so not x1 to 0, and that's basically saying this is my vertex cover. Yes, can I continue? So now suppose you say, okay, I don't want software and I don't want graphs, I want circuits. Okay, so let's talk about circuits. Suppose, okay, design engineers have this tendency after using all the tools in the flow, they go and fiddle with the design. So they change gates, optimize here and there to get smaller area. And sometimes they make mistakes. For example, here, this is what, okay, this is a very simple example, but this is what you were expected to have, and some engineer went and changed one gate wrongly, incorrectly. Okay? Now, of course, when people are designing in a company like Intel or IBM, they have lots of patterns which they use to test the design. So for example, in this case, you put 0, 1, and of course, the valid output is to get 0, 0. Now what happens in the faulty circuit, you put 0, 1, and now you get the wrong result. So 0, 0 is not valid. Okay? So how do we model this with max-SAT? Well, hard clauses are the things I can trust. The input values and the output values are for sure true because those were tested extensively. The things I'm not going to trust are the CNF representation of the circuit. Okay? So basically, I would like to satisfy as many of them as I could, but if there is a bug, I cannot satisfy all of them, right? So basically, so my objective is to maximize the satisfied clauses. so the circuit gates, and the things I cannot satisfy tell me there are bugs here. Okay. Now, more examples very quickly. So another problem is what's called binet covering. You may wonder, oh, is this important? Yes. I just put here 2 applications. I can easily list, let's say, 20 applications. Okay. So basically, it's very similar. We have a cost function, and then we just want to have a set of clauses we need to satisfy. So what is the virtual max SAT formulation? We've seen this before. So basically, we have hard clauses, the clauses of the original problem, and then we have weighted soft clauses, basically saying, well, I would like not to put x1 to true because that has cost, and I'm representing that with cost Cj. And of course, if I have no costs or unit costs, basically it's partial max SAT. So now let's talk about algorithms. So how do we solve these problems? And of course, notice that here we are trying to do what people are doing also in SMT. We are trying to capitalize on the good SMT technique, the SAT techniques. So one trivial approach is we can just do what is called iterative upper bound refinement. So basically, suppose you are given by chance some value b, which you know is an upper bound on the cost function. So you know that you can satisfy the constraints and get an upper bound of p. So basically, you can create a new constraint saying, well, what I would like to have is the cost function should be less than or equal to b minus 1, because b I know I can get. Yes? So basically, I now solve with the pseudo Boolean solver, or I encode to SAT. And if it's SAT, then, well, I've improved my upper bound to b minus 1. And I repeat this while it is SAT. When it becomes unsat, I know exactly what is the pseudo Boolean solution. Yes? Okay. Now, other ways to do this, we can also do iterative lower bound refinement. So instead of going through SAT instances, we go through unsat instances. And we can do it plain or unsatisfy what's called core guidance. I'm going to talk about that later on. And of course, we can do binary search on the values of the cost function. And here you can see that many people have been studying these things over the years. Okay. Finally, we can do what some of you would say, well, just do branch and bound search. And we've tried that 11 years ago. And so basically, we maintain an upper bound on the optimum solution. We just search and compute estimates of the lower bound. And every time the lower bound is greater than or equal to the upper bound, we just bound the search and backtrack, right? And of course, we integrate all the SAT techniques. We tried all of this 11 years ago, and still the best approach right now is just iterative upper bound refinement. Okay? Question? Yes, please.
It's best. So the top one is best for. Does it depend on the profile?
Yes. Yes. Suppose this is your interval. So these are the range of values. So that one works well when you are close to the maximum values. You don't have many iterations. This one works well when you are here, near the minimum possible value.
Right, when the core,
yes.
When the core is small.
Yes, I'm going to talk about that later on, yes. And so, of course, when everything else fails, you can try binary search. And some people, I just put Fu and Malik, but for example, there was a paper at TACUS 2010 about this. So, of course, there is a lot of interest on how you tackle these problems. And so binary search was reinvented again in 2010, trying to get the best possible performance. Okay? And, of course, in this case, it was for SMT. Can I go? Continue? Okay, so how do you tackle max SAT algorithms? So you have dozens of publications on doing branch and bound search. So you can use sophisticated lower bounds, basically finding the number of unsatisfiable clauses. And then you use some of the SAT techniques, unit propagation, finding cores like Nikolai said, or you can use dedicated inference techniques, for example, a modified resolution rule. And what is the bottom line? Well, you cannot use the techniques that have been shown so effective for SAT and SMT. You cannot do unit propagation, and you cannot do unrestricted closed learning. And there is no conflict here. Here you use this just to estimate the lower bound, but you are not solving the problem. So you cannot usually use unit propagation. Other approaches, you can translate to pseudo-Boolean algorithms I mentioned in the previous slide, or you can have core-guided algorithms like Nikolai into the end. So what am I going to talk about now? I'm going to talk about core-guided algorithms. Oh, not yet, sorry. So how do we solve, so let me go back. So that's why the two are in blue. I'm going to solve this one first and then this one. So how do we solve max SAT with pseudo-Boolean? It's very simple, and this is another form of encoding. So suppose you have given a formula with n variables and m clauses. All of them are solved to simplify. So you modify the problem, you replace each clause with a relaxed version. Okay, so you had one relaxation variable for each clause. And basically, this means that if you have m clauses, now you have n plus m variables. So it's trivial to satisfy this modified formula by assigning the relaxation variables to 1. Essentially, you are saying, I discard all the clauses, right? Yes? So let's see how do we do this for this example. So all these clauses are soft. And so how do I modify the formula? I relax each of the clauses. And so it's easy to satisfy all of them by setting the relaxation variables to true, right? But of course, this is not what I want. I would like to relax as few as possible clauses. So basically, what I'm going to do is iteratively solve a modified a SAT problem where I have the relaxed version, and then I have a cardinality constraint saying I would like to, at most, relax k clauses. And so I start with k equals m minus 1. So m is the number of clauses. Why do I start with m minus 1? Can anyone tell me? Yes? We know the answer, because for m, it would be relaxing everything. So it's trivial. So we start with m minus 1. And then we decrease the value while we can satisfy that formula, and stop when it becomes unsatisfiable, and then return k plus 1. So let me show you very quickly. So the modified formula, as I showed in the previous slide, is at 1. The possible values are k equals 2, 1, and 0. And of course, I'm not going to try, of course, I don't need to try 3 because that would be trivial, as I said. And so basically, it's satisfied for k equals 2 and 1, and satisfied for k equals 0. So the solution is 1. So that means I need to relax one clause. Okay? So this is right now one of the best approaches for solving max-out problems. So basically, you do pseudo-Boolean. What the hottest topic in the last 3 years is core-guided max-out. So we use all the techniques that are good for max-out. So this is the example. We started from 12 clauses, and just because this is going to grow, I replaced the disjunction with commas, the same thing, not a problem. And the first thing I do is call the SAT solver on this. So as I showed at the beginning, those 6 clauses are a core. So what I'm going to say is, what does this mean? This means I cannot satisfy the 12 clauses, and those for sure I need to relax one of them. Yes? Which one? I don't know, right? So what I'm going to do is relax all of them and put a cardinality constraint, saying, well, I just want to relax at most one of them, because I know for sure I need to relax one of them. I don't know how many. And so I'm going to say, well, the number of things I can relax is at most 1. Yes? Now, okay, so what's the next step? Then we call the SAT solver again. And he comes back and says, oh, I cannot do it again. And it's clear it cannot do it, because think over there, if you discard the relaxation variables, you get not x2. Here you get not x5, and here you get x5, and there you get x2. So you are going to get, and of course then you connect everything through this cardinality constraint, and you have your unsat core. Okay, so we cannot do it. So we get this is the unsat core. So we relax the soft clauses. Notice that, of course, this we don't touch. We relax the clauses again and put another cardinality constraint. And so what we do next? Well, call the SAT solver again. It comes back and says, well, yes, I'm fine, I can do it. So what is the conclusion? Come on. So basically, I relaxed once because I could not satisfy it. Then I relaxed again because I could not satisfy it. What is the conclusion? Joseph is looking at me. I need to finish this. So what is the conclusion? Okay. So basically, the max-out solution is the size of the formula minus the number of iterations. It's 10. Why? Because I need to relax 2 clauses. I need to relax one, then I need to relax the other one. So that's my max-out solution. Okay? So to summarize, clauses are either soft or hard. Okay? So for everything that I generate with cardinality constraints are hard clauses. And while I find unsatisfiable cores, I'm going to add fresh variables, relaxation variables, to the soft clause in the core. Add a new cardinality constraint, iterate, and then when I'm done, this is the solution. So basically, the interpretation is the minimum number of clauses that I have to relax to make everything else satisfiable. Okay? So this is really, really hot. Why? Because it works very well for practical problems. So for design debugging, this is the way to go. And for software package dependencies, this is also the way to go. Okay? So, of course, throughout the talk, I was using cardinality constraints and pseudo-Boolean constraints a lot, right? So the question, and I also mentioned, okay, actually, you need to encode to SAT. It's different from SMT. In SMT, you have your dedicated processing. It works well. Here, it does not. So how do we do it? So let me go very quickly. So basically, what I would like to do first is, suppose you are given this constraint. So the sum of the variables is less than or equal to k, and the special case is the sum of the variables is less than or equal to 1. So how do we encode this to CNF? So solution number one, you don't even encode. You just use a pseudo-Boolean solver. But the problem is, and it is shown in practice, it's very difficult to keep up with the advances in SAT technology. So all solvers that are native, that you handle these cardinality constraints natively, have not updated the SAT solver since 2006. So it's impossible to keep up with SAT solving technology unless you have a dedicated group that does that, right? And so what has also been shown is that if it's just testing SAT and SAT, the best solvers encode to SAT. So how do we do this? Solution is we just encode everything to CNF and use a SAT solver. So let's see. How do we do this? It's a very simple case. Suppose the sum of the variables is equals to 1. How do we do it? We require, well, it has to be less than or equal to 1 and greater than or equal to 1. That's easy. How do we encode? It has to be greater than or equal to 1. Well, that's easy also. It's just a clause. One variable is enough. Yes. Now, the hard part is, how do we say that the sum of variables is less than or equal to 1? And basically, there is a host of approaches. And so over the years, so this is the naive. You don't use auxiliary variables. You try all possible pairs. Of course, if you have, for example, if you have 10,000 clauses here, this would be impossible to do. You can use a sequential counter bitwise, etc. Of course, I'm going to briefly say how you do bitwise because it's really, really elegant a solution. Don't get desperate. It can be understood. So basically, we do the following. We start by creating auxiliary variables v0 to r minus 1, where r is the ceiling of the logarithm of n. And let's assume it's just the power of 2 to simplify things. Okay? And basically, with each variable, we associate a binary representation of j minus 1. So if it's xj, it's the binary representation of j minus 1. And then we just create these clauses where pi is, if the binary representation of j minus 1 is 1, we put vi in the clause. Otherwise, we put not vi in the clause. And let's see an example to see how it works. So suppose you want to encode x1 plus x2 plus x3 less than or equal to 1. Okay? Yes? How do we do this? Basically, x1 we associate 0, x2 1, x3 2. And so the binary representation is 0, 0, 0, 1, 1, 0. And so basically, the encoding is shown on the right. What does it mean? Suppose that this variable is 1. Suppose that this variable is 1, x1. What happens over there? If x1 is 1, what happens to the clauses? Basically, this is satisfied, this is 0, this is 0, so I must have v1, v2, sorry, v0, v1 equals to 0. So basically, if this variable is true, I must encode this. How many encodings can I have? Well, I can only have one encoding. So if this one is true, the others cannot be true. That's it. Okay? And of course, if all the variables are 0, not a problem, I just put any assignment. That's fine. Why? Because I'm satisfying all the clauses. It's done. Okay? So it's very easy to understand. Another one, and I'm going to skip this one because so this is another. As you can see, has been a steady improvement over the years, and improvement also in the quality of the encoding. I have but 5 minutes. Yeah, I prefer to go to the next one. Okay, so basically, it's a very nice recursive definition, the sorting networks, and basically. This is for this example. Basically, it's just a sequence of merge operations where each merge operation is just and or. So it's very, very elegant, and it promotes propagation. So it works very well in practice. Okay. So this was developed into 68. It has been improved over the years, and right now, let me go back a few slides again. We can get n log squared of k, where k is the right-hand side. Okay. So it's quite good in practice. Okay. Now, I'm almost there. So how do we do pseudo-Boolean constraints? This is the most general form. So what is a pseudo-Boolean constraint? Basically, again, coefficients, variables, right-hand side. And so people have been studying this for, for a long time. But in 98, Warner's developed this linear encoding, very nice, and it's linear in the size of the number of variables in the constraint. The problem, and this is really important, it does not guarantee our consistency. So it does not derive all possible consequences if you assign variables.
Why is the problem?
Well, because you want to propagate. If you are using a SAT solver, you really want to propagate.
We know that encoding which enforce our consistency in SAT are not necessarily better.
Yeah, I know. It's not. I cannot prove it's always better. I can give you 1,000 benchmarks, and in 900 it will be better. So in practice, it is known that if you do this, it does not work. Okay, and people have been studying this because they know this. They have tried other approaches, and notice that until here, so BDD's worst case exponential number of clauses was suggested in 2006, and then 2009, and now more recently 2011. And this is a paper that is not even published. It's going to appear in June. So we see that, well, here, basically, the number of, here it's going to be quartic. And here, finally, it's quartic. But here you have a log n, and here you don't have the log n anymore. So people basically show that you can do encoding of this for SAT, maintaining our consistency in polynomial space, which is an amazing result. Okay. Now, what I'm going to do is use BDDs, and I think it's a very intuitive example to show the type of things we are studying. So, suppose you want to encode 3x1 plus 3x2 plus 3 less than or equal to 3, and we are going to basically construct a BDD that says what is valid and what is not valid. So, let's see. So, we start with x1. So, if you put 0, so basically we have two possible values, yes? So, let's see. We put 1. What happens if we put x3 equals 1? Up there, what happens? Basically, 3x1 is now 3, so basically the others have to be 0. So that's what I'm saying. The only way to satisfy is to have 0. Anything else will be inconsistent. And if I put x1 equals 0, well, then I try x2, and if x2 is 0, then I'm happy. If x2 is 1, well, I cannot have x2 equals 1. And if it's 0, I'm happy again. So basically, I do this implicitly, and then I say, well, now for each node, I'm going to put an ITE operator, if then else operator, which some of you, I'm totally sure, know what it is.
What exactly is 3x1?
So basically, I'm multiplying 3 by x1.
Is it Boolean?
Yes, x1 is Boolean, 3 is not. Okay, so basically, that's why we call it pseudo-Boolean. The variables are Boolean, but then I have complete freedom for the coefficients. Okay, and basically, here I'm just encoding what is valid and what is not for my constraint. Okay. Now, basically, for each node in the BDD, I put an IT operator. Saying, well, if x, basically, I plug in these values. Okay, and then, of course, I want encoding to be consistent. That's it. Okay. Now, notice that I start from this symbolic representation. Now I have a Boolean circuit, which we know how to encode to CNF. And so basically, after doing some simplification, in this case, this is what we get. These are 2 gates, and this is a slightly more complicated Boolean operation, but still encoding to circuits to CNF then is very easy. So let me try to summarize what I've been talking about. So everybody knows the success of Boolean-based decision procedures. There was a talk on Z3. Yikes is also well known. Bar's logic tools. At a lower level, Minisat, Picosat, and there are a host of practical applications. Okay, and of course, Nikolai talked about many of them. Boolean-based optimization is still upcoming. It's a promise. I talked about MaxSat and pseudo-Boolean optimization and mentioned many other possible ways of doing optimization. And then I also mentioned several, and I believe there will be many, exciting applications. So software package upgrades is one example, and I went through this in some detail. Design debugging is another example, and I also went through this in some detail. Now, more interesting for the audience would be to say that bug localization in C code is going to be shown. I'm not sure, when is PLDI? June. So in June, there will be a paper on showing how you can do bug localization in C code with MaxSat. Okay, so it's not just a very theoretical problem. It has a very practical application. Okay, so this is done by Rupak Majumdar and a PhD student. And of course, there are many lines of work of research work in this area. Why? Well, we can do core-guided approach. I just mentioned one algorithm. We have actually studied more than 10 algorithms by now. We talked about CNF encodings. I showed that there is a clear evolution over the last 5 years, new encodings, very promising encodings. And finally, I think a nice line of work is to integrate with the standard ILP approaches of relaxation-based or, for example, Fourier-Motzkin. And that's it. Thank you very much. There is one.
Where?
See, I'm not sure if I won't use the page.
I'll repeat, yeah.
So, first question, you had a slide with several methods used for the sum of the xi less than or equal to 1.
Yes.
Which one was worked best on your benchmarks?
So I decided not to give results. I have many results. The one I showed, the bitwise, is the best one right now.
The in log.
Yes. Oh, so I was talking less than or equal to 1. For less than or equal to k, right now is the cardinality networks, n squared log k.
So cardinality network.
Yes. Developed by Nivenhuis group in Barcelona. For pseudo-Boolean in general, nobody knows. Why? Because most of these recent encodings have not been really studied in practice.
What's the how large are the cardinality networks?
Okay. Yes. So
space overheads.
Yes.
When you add them to the encoding of your benchmark.
Yes. So basically, the question is, how large are these constraints? Are they really large or not? And the answer is, they can be fairly large. Let me give you an example. For design debugging, basically you pick a huge circuit, you encode everything to CNF. So we can easily have, let's say, 4 million clauses.
So did anybody
and
these clauses incrementally?
Well, you don't know a priori, so you just have all of them, because this is a circuit that is failing. But let me give you an example. So you have 10 million, sorry, the largest one, let's say around 4 million clauses, and then you want this to be less than or equal to 200. So this is a huge cardinality constraint. It's essentially you need very effective approaches to solve this problem. So I don't have a board, but what I'm saying is that 4 million.
You claim that in the limit you were going to add all these clauses anyway.
Yes. Well, the pseudo-Boolean-based approach would do that exactly. Before talking about core-guided, the pseudo-Boolean does exactly that. So you relax everything and then says less than or equal to 200. So it's 4 million relaxation variables, sum less than or equal to 200. That's a very complicated cardinality constraint. So we are talking about very serious optimization problems, yes.
Any other questions for the speaker? No? Okay, so it's up to me now. Thank you, Joe.
Thanks.
Okay, this is the last talk. I'll try to be short. Okay, I have 20 slides, I think. So I'm going to talk about parallelism in SAT. So you know why SAT and SMT are important from the previous talk. SAT is a low-level engine for SMT. SAT and technique are applied in Maxim technique, as we have seen. And of course, I cannot give in 20 minutes an overview of parallelism in SAT. I'm going to focus on one problem that I believe is very important, which is the trade-off between cooperation and computation between parallel SAT engines. Okay. So the motivation is well known now. We know that the architecture of the microprocessor has changed, which brings to two facts. In fact, since the clock frequency are stalling, that means that existing sequential software will not be getting faster just freely because just you are just changing your machine. At the same time, we know that the density of the transistor is still improved, so therefore we can put more transistor on the same surface, and therefore one way to have scalability now is to put more computing unit on the same surface. Okay.
So this is a technological motivation to move towards parallel SAT. I believe that there is an algorithmic motivation, which is debatable, but I believe that sequential algorithms are hard to improve. Every year we see some improvement, but it's not what we have seen in the past. It's not orders of magnitudes. And there is we can combine this with the fact that since SAT was successful in verification in the last 10 years, we see that many other domains are trying to apply SAT to different problems, optimization problems, in general, very ambitious problem where eventually the performance of SAT solver is not very, very good. This is a picture from the 2009 SAT competition where you see that out of 275, I think, problems, the best solver could solve up to something like 200. You see, so this is the number of problems on the x-axis. So that means that 1/3 of the problem could not be solved by any sequential SAT solver in less than 10,000 seconds, so in a timeout which is close to 3 hours. Okay? And if you look closely at this problem, many of them were coming from bioinformatics. So that's what I said previously. There is a change in the application domain, and eventually the existing SAT engine are not very good for that. So, okay, what is parallel SAT? In one slide, this is the current situation with parallel SAT. Today, the state-of-the-art parallel SAT solver are applying what we call a parallel portfolio, where we put several solvers in competition on the same formula, in competition and in cooperation, and we are going to see how they can cooperate. So that means that we are not in the classical parallel search settings, which is well known as a divide and conquer, where we split the search space, we balance it. It's really a different setting. So here you see the list of the last parallel SAT solver, and so Penning, Manisat, Sartagnan, etc. And all of them now applying this parallel portfolio framework or mechanism. So in 2 words, we have a workflow here about SAT and parallel SAT. So just to refresh the algorithm and to see where we are going. So you can start to do some pre-processing of your formula. Eventually, you branch on some variable. This decision is used by the propagation engine, which can make some deduction. If you meet a conflict, you use the implication graph to perform conflict analysis. This is going to produce a new clause, which is a redundant constraint on the problem. You are going to use that clause. You are going to reuse it to do more propagation in the future. But you are going to reuse it as well to back jump, which means that you are going to correct the list of decisions that you have done. You are also going to use it to improve the heuristic choice that you do when you select branching variables. And when you meet some cutoff on the number of conflicts, you are going to restart. So in a parallel SAT setting, you are going to export that clause. You are going to send that clause through some knowledge sharing mechanism, and we are going to focus on that, to the external world. So today, the external world means other solver in the parallel portfolio. Okay? And of course, you can receive conflict clause coming from the external world as well. And this is processed at that stage, and you can do 2 things. Of course, you can reuse it in the propagation engine. You will do more propagation. But it could be the case that this clause is conflicting with your current list of decisions, so you can directly use it to perform conflict analysis and eventually back jump, etc., etc. So in parallel SAT, I believe that today the critical point is this component here, this knowledge sharing mechanism, and we are going to see it with more details. So here is the situation. You have a portfolio with 2 engines. One of them is learning a conflict clause here, and it decides to export it, okay, to the second algorithm in the portfolio. So the problem that we have is that potentially we can generate an exponential number of conflict clauses. So one way to deal with that, and the traditional way to deal with that, is to put a limit. which is related to the size of the clause. So we are going to export the clause which are no longer than some static limit E. Okay? So we are going to export small clause, and therefore we will control the cost of communication and the trade-off computation communication. The good news is that when we export small clause, we export powerful clause because the power of a clause is inversely related to its size. So with a small clause, you print more than with a large one. Okay. So clause sharing in SAT is a special case of knowledge sharing in parallelism, and these are a couple of definitions to see where we stand, where we are. So in parallelism, we call knowledge the information which is generated during search, and knowledge sharing is made by the set of techniques and mechanisms that you use to exchange the knowledge in the parallel system in general. And of course, you face the traditional trade-off here, which is the cost of sharing. When you share, you have to stop, you have to prepare information that you want to share, and therefore you have to face, and you can also face communication overhead. When you do not share, eventually you miss constraints. Well, in our setting, we miss constraints, and we can perform redundant work. In a divide and conquer settings, which was the traditional settings of parallel SAT, if you do not share, eventually you have a task starvation, which means that some processing units have nothing to do. So you have to share sub-problems. So back to clause sharing. So as I said, it's a trade-off between the cost of communication and the benefit that it has on the search process. So to deal with it, that means that you need to find out what is the right static limit that you are going to use to export the clauses. So, and to do that, the first thing that you have to do is offline tuning to find out what is the optimal limit. So here is a set of problems from the SAT race. We have a portfolio with 4 engines here, and we try many limits. So when we do not share, we have this red curve here. This is the performance of the parallel solver. And you can see that when we push the limit to some high value, like 16, the performance is worse than with smaller limits. We can see that on this set of problems, the optimal limit is size 8. So that means that the best trade-off is to share clause up to size 8. Okay, but the problem is that you have to do that offline. You have to do this offline tuning. So the second problem with a technique like clause sharing in SAT and with static, based on the static size of the limit, is the following. So we call it saturation, and to illustrate it, we made an experiment with a sequential SAT solver where we took a family of problems, industrial problem, and we managed to plot here every 10,000 conflict the percentage of learned clause with a size less or equal to 8. And we start with a fairly high value, 16%, I think. And we see that after a while, after more than 1 million conflicts, we are below 3%. So that means that over time, the size of the clause that you learn is rising, okay, because you saturate the process. You can see this spike here. From time to time, it decreases and it goes up, etc. It's because in the back, you have the clause deletion mechanism, and eventually you can rediscover things. So if you take this fact into account, that means that eventually any clause sharing policy based on the static limit will stop, because eventually the clause will always become longer than your static limit. Okay. The third problem that we have with clause sharing is what we call the problem of the relevance of the search. So here we took, again, the sequential settings. We took one real problem. I forgot what it was. And we made this decision here. This is a set of decisions on the variables, positive decision here. And you can see that after less than 10 decisions, you split the formula into 2 components. So you might think that this is going to happen in a portfolio as well. You might have a situation where one algorithm is working on one component, which is completely disconnected from the search, from the problem explored by other algorithms. So in that scenario, if you share clause, it's completely pointless. You are not going to help each other. Okay? So to address this free issue, we define a technique which uses control theory to And I'm going to describe this technique in 5 slides. So we call it control-based close sharing. It was presented 2 years ago at ICHKAI. So here is the settings. So we have a portfolio with 2 cores. We are going to use dynamic pairwise limit to control close sharing between any pair of SAT solver. Here, the limit Eij will control the sharing between I and j. On a regular basis, each unit will perform a log-free revision of the incoming limit, which means that unit I here is going to update the limit used by unit j to send information. And we will have 2 objectives here in order to face the 3 problems that I have described. The first objective would be to maintain a throughput. A throughput is is an amount of information, an amount of code that we want to share in the system. And by maintaining a target throughput T, we want to address the problem 1 and 2 that we have seen. And the second objective will be to maintain a throughput T of a given quality. And by introducing a notion of quality, we will be able to deal with the last problem, which is the problem of the relevance of the search. So concretely, this is what is going to happen on this on the problem with 2 units. So we have a time window. We are at a step k-1 here. Unit I is receiving clauses from unit j. These clauses are respecting the actual limit. Okay. We reach time k, and unit I is going to update the incoming limit used by j here. Okay. And in the next time window, of course, j will respect the new limit, etc., etc. So it's very simple. So some definition, as I said, a throughput for us in this system is a number of foreign clauses that we want to receive between a time interval. A time interval is defined as a number of conflicts. Okay? And typically, the idea is that we do not want to receive more information than what we are able to produce, because we want to keep the identity of our search effort. So if a unit is performing alpha conflict in a time window, it is okay to accept from the outside a share of this alpha conflict, okay, like 50% of alpha. So we are going to do that now. We are going to consider at each timestamp tk the set of foreign clause rk received during the previous time window. If the size of this set is less than the targeted throughput, we are going to perform a uniform increase of the incoming limit. If it's more, we are going to perform a uniform decrease of the incoming limit. So now the question is, how do we update the limit? And that was the key point here for us. And to solve this problem, that's where we use control theory. And I want to illustrate this with a problem coming from networking. So in networking, they solve every day, they solve this TCP congestion avoidance problem, where the goal is to guess the available bandwidth available between a sender and a receiver. So there is a communication network. This network is full of capacity, restricted capacity. And you want to send information at a good rate. So you want to eventually maximize the communication rate. Of course, you have no idea about what are these limits here, what are these capacities. And of course, you are in competition with other people who are doing the same thing. So in TCP, they are using the following technique to guess the communication rate W. They apply a policy which is called additive increase, multiplicative decrease, which is doing the following. It is going to perform slow increase of the communication rate as long as there is no packet loss. Okay? The idea is that we try to probe for the right, for the available limit, bandwidth, in fact. As soon as there is as a loss is met, the policy performs an exponential decrease of the rate. And the idea is that when you have a congestion which is starting in the network, in order to quickly recover, you need to quickly stop communicating. Okay? So what's the relationship with parallel SAT? So we believe that with close sharing, when we increase the limit, eventually this can be very negative because you can receive a very high number of incoming clause. Okay? So we are going to apply an AMD policy. We are going to perform slow increase as long as the throughput is not met, and exponential decrease when we meet the throughput. So, and that's the first policy that we can present now, which is called AMDT. So when we have to update this limit here, we are going to consider the set of incoming clause Rk in the previous time window. If the size of this set is less than the targeted throughput, we are going to perform an additive increase of the limit between I and j here with some parameter b. If we overshoot the throughput, we perform a multiplicative decrease here of the new limit. Okay, we use the previous value each time, and we do that for each with each external unit. Okay, here we just have 2 units. Okay, so that was this policy will allow us to maintain a particular throughput. Okay. The second objective that we have is to maintain a throughput of good quality. And for that, I have to define what is the quality. So in our setting, we would say we are going to reuse one existing component of a SAT solver, which is the VSIDS heuristic, which is used to decide, to select the next variable to branch on. And it works like that. It is some kind of ranking of the remaining variables. And the idea is that unassigned variables with very high activity are going to be selected next, and therefore they are related to the future evolution of the search process. The activity is a value given to each remaining variable, and it is computed when you do conflict analysis. The idea is that when you do the conflict analysis, you see variables which are involved in the generation of the new conflict clause. Okay? And what you do is that you rise the activity of the variables which were useful to generate the new conflict clause. And the goal, by selecting variable with high activity, is to focus the search in the area where you have learned a lot of recent conflict clause. Okay? In some kind of intensification mechanism, and the activity of a variable is used to define how related is the variable to the recent conflict. Okay, and the idea is that you pick up as the next decision. Of course, you have randomization there, but the next decision is the variable with the highest activity. So we can see this heuristic information as a way to define the future evolution of a search process, because it defines the future decision, in fact. Okay? So we are going to define for unit I the maximum VSIDS activity as AI max, and we will define each time we receive a foreign clause C, we will define the set of literals of the foreign clause, the set of active literals, and it will be defined as the set of literals of that clause with a local activity which is at least half the maximum activity. Okay, it's a way to correlate the foreign information with what the core believes is important. With that definition, we will be able to define the set of clause received from J with at least Q active literals. Q is the targeted quality, that it's a parameter. So it's a set of clause received in the previous time window, such that they have at least Q active literal as defined before. And eventually, we can define the quality by taking this value against the overall number of clause received. So the quality is the percentage, and it tells us how related are the clause received from a particular SAT solver. Okay? So, and that gives an update to the previous AMD policy. So we are going to integrate the quality when we want to increase the incoming limit because we don't meet the throughput, okay? And we are going to take into account the quality when we want to decrease the incoming limit because we have met the throughput. The idea is that now the increase and decrease are not uniform anymore, but they are related to the quality. When we have to increase, we will increase more the limit which are linking the unit with foreign solver which are giving good quality information. And when we have to decrease, we will decrease more the limit with the solver we gives bad quality information. Okay? It's a way to adjust the policy, the IAMD policy. So very quickly, the evaluation. So the problem of the saturation that we have seen before, that was the approved policy where we could see that over time, the average size of the clause that we learn is rising. On the same problem below, we have, for a parallel portfolio of 4 cores, we managed to plot the average incoming limit. So it's the average between 3 values for each core in 4 colors. And then the average for the portfolio. And you can see that over time, since the average size of the clause which are produced is rising, and since the goal is to maintain a given throughput, automatically the incoming limits are increasing. Okay? And you can see that there is a behavior where it is increasing, decreasing, because we meet the throughput and we are aggressive on the decrease. It's multiplicative decrease, etc., etc. Okay? So in practice, what does it give? Let's see what we can do. So we have the SAT race here. We have 100 problem, and we have a parallel SAT solver, which was tuned offline with the best possible static limit. So a static limit of 8 is the best thing you can do on average on this set of problems. And we can solve 83 problems in some cumulative time here. So it's really trying to beat the optimal tuning. The first policy where we just try to maintain a throughput is given here in the middle. And you can see that by adjusting automatically with some throughput that we are targeting, we can solve 3 more problems. So 3 problems does not look very impressive, but in SAT, I mean, the last few problems are very hard to catch. And when we try the last policy that we have, when we maintain the throughput and the quality, we can solve 6 problems more than the optimal static tuning. So practically, it's very useful. It's a nice way to control the trade-off between cooperation and computation in a parallel system. So I'm done now. I just have a short conclusion. So today, I mean, this is one example of what is done in parallel SAT solving today. But to start at a higher level, SAT is important for many domains, for QBF, for SMT, and it has many application domains. So the current situation with parallel SAT is that divide and conquer does not work at all, and everybody is doing portfolio of sequential solver. Some people try to mix both approaches, but still it seems that portfolio are always better. And this portfolio, they compete and they cooperate on one formula. And of course, when you do that, you have to trigger, to adjust the trade-off between the cooperation and the computation that is done. We have seen a technique that we use, which is able to dynamically control the trade-off with respect to the problem. So a list of questions now for parallel SAT. So it seems that very difficult for a portfolio to scale beyond 8 cores. So this is one question that people are considering. How can we adjust the technique when we'll have to face, for example, 16, 32 cores? What can we do? Do we have to put some hierarchical structure in the portfolio? Many things are tried, and we have tried a few things. The second question, now I think it's a problem that we have solved, is the question of determinism. So SAT solver, parallel SAT solver used to be non-deterministic. That means that when you run them 2 times, you have 2 times, eventually you have 2 different solutions. But today we have a solution for that with a very good performance, which is equivalent to non-deterministic solver. Distributed search, which is a different scenario where you have a huge SAT formula that you want to split into pieces for many reasons, because eventually it does not sit on one machine, is a new is a promising domain, and we are working on that with Christophe as well. And of course, as we have seen, parallel SAT is just an extension of sequential SAT. So I believe it will be interesting to try to do something else, to completely rethink the sequential SAT architecture and to take advantage of the multi-core machine in a completely different way. So I'm done. If you have questions. No questions at all on parallel SAT? Yes? There is one if you want. Oops.
I didn't see a characterization as to the size and character of the parallel machines that you're using, and I'm wondering how much that influences.
Sorry, could you repeat?
I didn't see a characterization of the size and character of the parallel machines you're actually using in the benchmarks, and I'm wondering how much that might influence the approach.
Well, machines are defined by the organizer of the SAT competition, and so typically I think it's up to 8 cores. We see the limit when we reach the physical limit of the machine. If we run a portfolio of 8 cores on an 8-core machine, it's far worse than running a portfolio of 8 cores on a 16-core machine. You know, we see all these the limitation with the bandwidth, etc. So, and this is very difficult because then if you want to judge the strategies that you put on an 8-core portfolio, you cannot do it in an 8-core machine because what you will observe is not the quality of your strategies, but more the physical limitation of the machine. So today, yes, but typically I think the next competition is on 4 cores or 8 cores. I think 8 cores, and it is slowly moving, but.
The secondary, question is, if you know enough about that as well as caching size, then that can then influence the algorithm as well.
Of course, yes.
And thereby you could effectively parameterize this control system by architecture.
Yeah, this is a good point, yeah. We believe that, parallel architecture, they are not uniform today between, if you take an AMD computer or Intel-based computer, you observe completely different things, and we have seen that with the parallel portfolio. And doing dynamic adjustment like we do is a way to try to forget about that and to adjust. So one thing to do here, for example, the throughput T in that work is an input, is a given parameter, but ideally the throughput could be dynamic and defined in relation with the efficiency of the search process below. This is something that we like to do. This technique will be very interesting in a distributed scenario where you have several machines with several cores, and where the communication is very different between local communication or inter-machine communication. So in those scenarios, you can imagine that you can relocate search strategies. So if the limit is very high, if you are very close to the search effort done by some algorithm which is remote, it is worth relocating it on the local machine, etc. So it becomes some optimization problem, but we can imagine some low-level policy. We try to approximate a good solution there. Yeah, but we are facing the existing hardware limitation, etc. New question? No. Yeah.
Just a remark, not a question really. In my group, there is an attempt to make the core of EZADA for an interactive prover also parallel. So having a parallel classical LCF kernel. And actually we hit also the 8-core barrier. That's so Becarius Wenzel, who is doing actually the work, who's not here, could give you much more details than I can. But actually, we have the same, the 8-core barrier at the moment, which has, well, to do also with the entire stack of different phenomena that you have on the hardware, the runtime environment, and actually the core algorithms, and finally, and the observation seems also to be that if we want to get beyond, then it becomes a very pervasive problem. So little optimizations here, if considered just locally, do not really improve the entire stack of phenomena that you have in the entire implementation.
Yeah, thank you. Anything? No? We are done. Any questions for the previous speaker? Because we are going to finish the session. So what about the price of Z3? Did you have time to think about it, Nikolai? No, that was a joke, that's fine. Joao, don't worry.
The price? That's... yeah.
No, anyway, we it's a classical question anyway. So I'd like to thank everybody because it's Friday afternoon and it's very nice to be there for the last session on a very tiny topic. Thank you. Bye-bye.